Chapter 11, Force and Newton's Law. In this chapter we're going to take a look at Newton's three laws of motion to better understand motion, momentum, and inertia. We begin by taking a look at the objectives for today's lesson. Our objectives, the students will distinguish between balanced and net forces. Students will describe Newton's first law of motion, and students will explain how friction affects motion. Let's begin. On page 310 in your textbook, we begin by reading the section titled Force. A soccer ball sits on the ground, motionless, until you kick it. Your science book sits on the table until you pick it up. If you hold your book above the ground and let it go, gravity pulls it to the floor. In every one of these causes or cases, the motion of the ball or book was changed by something pushing or pulling on it. An object will speed up, slow down, or turn only if something is pushing or pulling on it. A force is a push or a pull. Examples of forces are shown in Figure 1. Think about throwing a ball. Your hand exerts a force on the ball, and the ball accelerates forward until it leaves your hand. After the ball leaves your hand, the force of gravity causes its path to curve downward. When the ball hits the ground exerts a force, stopping the ball. A force can be exerted in different ways. For instance, a paperclip can be moved by the force of a magnet exerts, the pull of Earth's gravity, or the force you exert when you pick it up. These are all examples of forces acting on the paperclip. Throwing a ball, shooting a basketball, hitting a golf ball is all examples of you applying a force to something and causing something else to move. Can you think of any other examples? Obviously, the one in the picture shows a golf club hitting a golf ball, and the force of the ball and the club striking each other causes the ball to move. You have a massive, huge magnet on the bottom of page 310 picking up pieces of metal. A magnetic force is something that can cause certain pieces of metal to move. But a force can be exerted in different types of ways. Let's take a look at on page 311, combining forces and balanced and unbalanced forces. Combining forces. More than one force can act on an object at the same time. If you hold a paperclip near a magnet, and the magnet and gravity will exert forces on the paperclip. The combination of all the forces acting on an object is the net force. When more than one force acts on an object, the net force determines how the motion of an object changes. If the motion of an object changes, its velocity changes. A change in velocity means the object is accelerating. How do forces combine to form the net force? If the forces are in the same direction, they add together to form the net force. If the two forces are opposite direction, then the net force is the difference between the two forces, and it is in the direction of the larger force. At the top of the page, you have two young scholars who are pushing on the door against each other. In the first one, the door is not moving because the forces are being exerted in opposite directions. Therefore, the net force cancels each other out. In the second picture, the door is closing because the force of the student on the left is greater than the force of the student on the right. So when those forces are even working against each other, the one with the larger force is going to be the one that wins or moves the object in that case. The net force, again, is the combination of all the forces acting on an object. If one of those objects, or if that object is still moving because one of those forces is larger than the other, then we have what's called balanced and unbalanced forces. A force can act on an object without causing it to accelerate if other forces cancel the push or pull of the force. Look at Figure 2. If you and your friend push on a door with the same force in opposite directions, the door does not move. Because both of you exerted a force of the same size in opposite directions on the door, the two forces cancel each other out. Two or more forces exerted on an object are balanced forces if their effects cancel each other and they do not change the object's velocity. If the forces on an object are balanced, the net force is zero. If the net force is not zero, the forces are unbalanced forces. Then the effect of the forces don't cancel and the object's velocity changes. So you've got balanced forces, or two or more forces exert an object cancel each other and something doesn't move. You've got unbalanced forces when the net force is not zero and the force exerts on the object and the object moves and has velocity. Now, here's how you might experience balanced forces and unbalanced forces, and part of your assignment is to go out and try these things. Find somebody to arm wrestle and see who can exert the greatest force, or find somebody to tug a war with you with a towel, see who can exert the greatest force. You'll be able to really quickly learn what balanced and unbalanced forces are by taking on those two types of activities. Newton's first law of motion. If you stand on a skateboard and someone gives you a push, then you and your skateboard will start moving. You will begin to move when the force was applied, and an object at rest, like on your skateboard, remains at rest unless an unbalanced force acts on it and causes it to move. Because a force had to be applied to make it move, you and your skateboard were at rest. You might think that a force has to be applied continually to keep an object moving. Surprisingly, this is not the case. An object can be moving even if the net force acting on it is zero. The Italian scientist Galileo Galilei, who lived from 1564 to 1642, was one of the first to understand that a force doesn't need to be constantly applied to an object to keep it moving. Galileo's idea helped Isaac Newton to better understand the nature of motion. Newton, who lived from 1642 to 1727, explained the motion of objects in 3 rules called Newton's laws of motion. Newton's first law of motion describes how an object moves when the net force acting on it is zero. According to Newton's first law of motion, if the net force acting on an object is zero, the object remains at rest. Or, if the object is already moving, continues moving in a straight line at a constant speed. What's often associated or described as Newton's first law of motion, an object at rest will stay at rest, an object in motion will continue to move or will continue in motion. This is oftentimes described as the law of inertia because we say inertia is the object's ability to resist motion or something not wanting to move. So inertia is described here if something isn't moving. For example, your textbook, wherever it's sitting in your room, on your desk, on the kitchen table, if it just sits there, it's never going to move. It's never going to have anything act on it until you come and open it up and start, obviously, the process of learning and reading through it. But if something doesn't have anything acting on it, it's going to sit there. That's the law of inertia. Newton's first law of motion says if nothing acts on it, it's going to continue to stay at rest like a book on a bookshelf. But if something does act on it, if something pushes or pulls it, then there's going to be some type of motion. Now there's one thing that can stop that motion, however, because the ideal law says that it'll move in a straight line at a constant speed. But it doesn't factor in things like friction and things like gravity, forces that would stop it from actually moving. Friction is one of those forces. Galileo realized that motion of an object doesn't change until an unbalanced force acts on it. Every day you see moving objects come to a stop. The force that brings nearly everything to a stop is friction, which is the force that acts to resist sliding between 2 touching surfaces as shown in figure 3. Friction is why you never see objects moving with constant velocity unless a net force is applied. Friction is the force that eventually brings your skateboard to a stop unless you keep pushing on it. Friction also acts on objects that are sliding or moving through substances such as air or water. Friction is the force that brings nearly everything to a stop. There are 3 different types of friction. Although several different forms of friction exist, they all have one thing in common. If 2 objects are in contact, friction forces always try to prevent an object from sliding on the other object. If you rub your hands against a tabletop, you can feel the friction push against the motion of your hand. If you rub the other way, you can feel the direction of friction change, so it's again acting against your hand's motion. What do the different forms of friction have in common? Well, those 3 different forms are static friction, sliding friction, and rolling friction, and all of them have in common the idea or the objective to bring something to a stop because of the contact the 2 surfaces have together. Older ideas about motion. It took a long time to understand motion. One reason was that people did not understand the behavior of friction, and the friction was a force. Because moving objects eventually come to a stop, people thought that the natural state of an object was to be at rest. For an object to be in motion, something always had to be pushing or pulling it to keep the object moving. As soon as the force stopped, the object would stop moving. Galileo understood that an object in constant motion is as natural as an object at rest. It was usually friction that made the object slow down and eventually come to a stop. To keep an object moving, a force had to be applied to overcome the effects of friction. If friction could be removed, an object in motion would continue to move in a straight line with constant speed. Figure 4 shows motion where there is almost no friction. You've got an air hockey table that actually pushes air through the different parts of the table with these tiny little holes that pushes the plastic puck up a little bit so that it actually slides across that surface a lot better. In the actual game of hockey, obviously the surface is really, really slippery, ice itself, and then you have a really sharp blade on the bottom of your ice skate that allows you to slide across that, reducing friction. 3 different types of friction on page 314 and 315. Static friction. If you've ever tried pushing something heavy like a refrigerator, you might have discovered that nothing happened at first. Then, as you pushed harder and harder and harder, the object suddenly will start to move. When you first start to push, friction between the heavy refrigerator and the floor opposes the force you're exerting and the net force is 0. The type of friction that prevents an object from moving from when a force is applied is called static friction. Static friction is caused by the attraction between the atoms on the 2 surfaces that are in contact. That causes the surface to stick or weld together where they are in contact. Usually as the surface gets rougher and the object gets heavier, the force of static friction will be larger. To move the object, you have to exert a force large enough to break the bonds holding 2 surfaces together. Sliding friction. While static friction acts on an object at rest, sliding friction slows down an object that slides. When you push a box over the floor, sliding friction acts in the direction opposite to the motion of the box. If you stop pushing, sliding friction causes the box to stop. Sliding friction is due to the microscopic roughness of two openers, such as in Figure 5. The surfaces tend to stick together where they touch. The bonds between the surfaces are broken and form again as the surfaces slide past each other. This causes sliding friction. Figure 6 shows the sliding friction is produced when the brake pad in a bicycle brake rubs against the wheel. In Figure 5, there's a zoomed in look of the tray sliding across the rail for picking up for lunch, and it shows a really microscopic zoomed in view of what those surfaces actually look like. Even though they look smooth, at that microscopic level they have these little edges that are going to get caught on things and cause that sliding friction to slow things down. The other idea that has come into play in terms of our development of technology to fight friction is, well, if things don't slide across it because it's too heavy or because there's those uneven surfaces that aren't very smooth, well, let's make something that rolls across it. But there is still contact, so we call this portion rolling friction. If you're coasting on a bicycle or a skateboard, you slow down and eventually stop because of another type of friction force. Rolling friction occurs when an object rolls across a surface. It is rolling friction between the bicycle tires and the ground, as in Figure 6, that slows a moving bicycle. The size of the rolling friction forces usually is much less than the force of sliding friction between the same surfaces. This is why it takes less force to pull a box on a wagon or a cart with wheels than to drag the box along the ground. Rolling friction between the wheels and the ground is less than the sliding friction between the box and the ground. If you'd like to complete the self-check on the bottom of page 315 to make sure that you've got a good understanding of Newton's first law of motion, you can. Otherwise, a really good way to make sure that you've got a good understanding is to go back to our objectives. Remember our objectives from the beginning of today's lesson? You will distinguish between balance and net forces. So if something is caused to move or if it's sitting still, those ideas of balance and net forces was again found on page 311. Next, we learned about Newton's first law of motion, found on page 312. And then last, looked at the different ideas of how friction tries to bring things to a stop and how it affects motion. That concludes our study of Newton's first law of motion and the beginning of chapter 11. Thanks for completing your reinforcement as today's homework assignment. God's blessings.